Welcome to our next discussion on logic, this one about logical equivalence and De Morgan's laws. So the only objective we really have here is to determine the validity of formal arguments, kind of what we've been talking about in a lot of these videos, but now we're going to kind of get into the nut and bolts of it. Switching the order of the simple statements in conjunctions and disjunctions makes no difference to the truth table. So what that means is if you switch A and B to B and A, or if you do, P or Q to Q or P, that doesn't change anything because it doesn't matter, right? An and is always false unless both things are true, so it doesn't matter in which order you do it. And an or is always true unless both things are false, so again, it doesn't matter in which order those are in. But A implies B is totally different than B implies A. When you switch the order of those, you do in fact get different things. So when you're given a conditional statement, you can think of the converse, inverse, and contrapositive of the original statement as when you are switching things around and negating things. There's a lot of vocabulary when you're dealing with logic, with the converse, the inverse, the contrapositive. They talk about the conditional. They talk about disjunction and conjunctions and all these words. Try not to get caught up in the minutia of the language unless you have an instructor that requires you to memorize those words. It's not that important that you know what an and or an or is called. It's more important that you understand what they do and how they work. So you've got your conditional, P implies Q. If you switch the direction and say Q implies P, that's called the converse. If you keep the original direction of P implies Q, but you negate both of those things, that's called the inverse, right? You've taken the negative, you've inverted their truths, so to speak. And then if you do both, change the direction and change the signs, it's called contrapositive. Those are kind of tough to memorize, so I would imagine you're going to want to put them in your notes somewhere if it's something that you're going to have to worry about in the future. And then, of course, the biconditional just means if and only if. That's where P implies Q and at the same time Q implies P. So really, in essence, just so you understand how it's working, this is really the same thing as P implies Q and Q implies P, right? So if you were doing a truth table, that's what you're doing. You really have an A and B situation where A is P implies Q and B is Q implies P. So it becomes a very multi-step process to figure out the truth table for a biconditional. Okay, let's see if you can write the converse, inverse, and contrapositive and biconditional variations of this famous statement by Marilyn Monroe, where she said, if you give a girl the right shoes, then she can conquer the world. You can see how that's an if-then. So A, right, the first statement is you give a girl the right shoes. B is she can conquer the world. So there you have A implies B. The converse is B implies A. And it's always easier, guys, to put the symbols in, then, do what you have to do to the symbols, and then put the words in, rather than just trying to go straight from the words to the words. That can get a little complicated, especially since English is a little iffy in places. So now when you have B implies A, you just have if she can conquer the world, then the girl was given the right shoes. And then not A implies not B just means you have to negate both of those original statements to do the inverse. If you do not give a girl the right shoes, she cannot conquer the world. The contrapositive is you have to negate and switch. So if she cannot conquer the world, then the girl was not given the right shoes. And then the biconditional is an if and only if. Give a girl the right shoes if and only if she can conquer the world. It's kind of silly, but biconditionals, you're basically just throwing the phrase if and only if into it. Okay, how about writing the contrapositive of a conditional statement? If I cannot find my phone, then it is in the car. So what is A? A is not I cannot find my phone. Remember, we talked about this before. You always have to set your original statements as the positive version of the statement. So A becomes I can find my phone, and B is it is in the car, i.e. my phone is in the car. So that means that this original phrase, if I cannot find my phone, isn't A, it's the negation of A, or squiggle A, right? It's the opposite of A. So this original setup, right, this original statement is not A implies B. So now if you're going to do the contrapositive of that, well, the contrapositive is flip directions and flip signs. So when you flip directions, B implies not A, and then when you flip signs, you get not B implies A, because not A, right? It's like double negatives. A negative times a negative gets you back to positive. You just get A. So now all you're going to have is say, sorry, all you're going to do is put the English into this one and say if, right? If B, or sorry, if the opposite of B, then A. So if my phone is not in the car, then I can find my phone. And here it is written all out like we just did. Okay, how about a biconditional statement? We'll let the statements C and D be I am breathing, I am alive. So the biconditional statement is C implies D at the same time D implies C, or basically C if and only if D. So I am breathing if and only if I am alive. Skill check. Write the inverse of this statement and see if you can get it correct. Try obviously not to look at the bottom of the slide first and then come back and check it. All right, were you able to get that if you're going to take the inverse of if I cannot find my phone, then it is in the car? The inverse, remember, is the negation of everything. So cannot becomes can, and it is in the car becomes it is not in the car. All right, good job. Truth values for all of these statements. So we start with the standard A and B, and then we just write down the negations of A and B just so we have them there for reference. Okay, the conditional, we've already seen this, right? A implies B is true everywhere except for when the first part is true and the second part is false, which is this case right there. Okay, now the converse, we're now going in the opposite direction. B implies A. Same rules apply. It's only going to be false when now B is true and A is false. So this is good, this is good. Here's the bad one, and that one's fine. So true, true, false, true. Now the inverse, we now do the negation. So this one implies this one. And we can see that this is the only problem, right? True implies false. Contrapositive is we're going in the opposite direction. So not B implies not A. And so this is going to be the problem where that true implies that false. And then biconditional is basically where you do an and. So the biconditional, put this in here for you. This thing is really just these two things put together with an and. So you're just going to do an and between this. So true and true is true, right? False and true is false. True and false is false. And then true and true is true. And that's how you can do the biconditional from scratch. Now, once you have done that, you notice that the pattern will always hold because you can now go back and look at the originals and see that it was true when they are the same, right? So if they're both true or both false, then the biconditional is true and it's false otherwise. And that's kind of the generalization of a biconditional if you want to try and memorize that. Otherwise, just do the table each time. Okay, biconditional statements always read if and only if are true, like I said, only when they have the same values. Logically equivalent statements are statements that have the exact same truth table values for all situations, and we use this funny little symbol. It basically is just a triple equals, right? It's an equal symbol with a third line instead of two to say that they're mathematically or logically equivalent statements. Now you'll notice that nothing in this table was logically equivalent except for these two here and then this one and this one. So logically equivalent statements, even though they all four have just one false and the rest are true, they're not logically equivalent. The only ones that are logically equivalent are the ones that are in the exact same shape, right? Everything's in the same places. So true, false, true, true, and true, false, true, true, those two things are logically equivalent. And then if we look at these two, right? True, true, false, true, and true, true, false, true, that means these two are logically equivalent. Okay? That's what it means to be logically equivalent. You can't just have the same number of trues and falses. They have to be in the exact same order. Find the other statements that are logically equivalent. Well, we've already done that. De Morgan's laws. Augustus de Morgan was an English mathematician and logician. He defined two very famous equivalent negations that we use a lot. And it's the idea that if you negate an and, you get an or of the negations. And if you negate an or, you get an and of the negations. You see the difference here? Remember your order of operations. First you do what's inside the parentheses, then you go outside. So this thing on the left is saying, first you do the and, right? Then you take the opposite of that. This one is saying take the opposite of P, take the opposite of Q first, and then do the OR of those two things. Two completely different things, but they're logically equivalent. And then the same happens when you do an OR first and then negate it. It's the same thing as negating the two statements and then taking an AND. How is that helpful to you? Well, it just will help you simplify some things with certain types of questions. Consider the following compound statement. It is not true that Jack and Jill went up the hill. So from the given statements, choose the statement that is logically equivalent. Which one do you think it is? Well, it's probably pretty hard to do it by just reading it. English can be kind of tricky. So it's best to pull out the pieces. This is an and. So there's my and. So it is not true that Jack and Jill went up the hill. So doesn't that mean that we're saying the opposite of P and Q, where P is Jack went up the hill, Q is Jill went up the hill. So this is Jack and Jill both went up the hill, right? Jack went up the hill and Jill went up the hill. In English, we would just say Jack and Jill went up the hill. And then this is just saying it is not true, right? Take the negation of it. So if we take the negation of that, isn't that the same thing as not P or not Q according to Morgan's law? And that means Jack didn't go up the hill or Jill didn't go up the hill. So Jack did not go up the hill and nope. It is not true that Jack and Jill didn't. Nope. Jack went up the hill or Jill went up the hill. No, we've got Jack did not go up the hill or Jill did not go up the hill. So do you see how D would be the logically equivalent statement here? And this is where I'm walking you through the steps of what you want to do. You always want to put some symbols in, represent the statements, write out what you have originally, use De Morgan's law, and then from that, bring it back to the statements and see which one matches that, and we get D. How about this? Determine which of the statements from example 4 is equivalent to neither Jack nor Jill went up the hill. Pause it, see if you can figure it out. All right, did you figure it out it was this one? Good. How about the negation of conditional statements? The negation of P implies Q is P and not Q. Because if you remember, that's the only place in the conditional that is false, right? The only time the conditional is false is when the first thing is true and the second thing was false. The first thing is true and the second thing is false, right? Not Q. So if we wanted to write the negation of if I go to Moss's dinner, then I get the triple stack pancakes. A is going to the dinner, B is getting the pancakes, so the negation would be go to the dinner and not get the pancakes. I go to the dinner and I do not get the triple stack pancakes. Okay, so that's our last negation. We can now negate anything and everything. If we want to negate this whole thing, you have to do it in pieces. If we want to negate that big compound statement, first we apply the negation to the conditional. And why do we do that? Because that's the biggest piece. It's kind of like working from the outside in. So when you negate a conditional, it's the first thing and the opposite of the second thing, right? So there's A and not this stuff. But isn't not this stuff we could use De Morgan's law if we wanted to? Couldn't we take this a step further and say it's A and then what happens to this? This whole big piece becomes not C or not D, right? That's what happens to that piece when you use De Morgan's law. So it basically becomes A and not C or not D. There you have it. All right, so negating everything. Negating ands, ors, and conditionals, pretty easy. We don't really negate a biconditional because it doesn't make sense. So you don't have to worry about that so much. And then remember, truth tables are your friends.